Hi folks, so we're now moving on to definitely some new physics. So make sure you really engage with this, and if you've got any questions, let me know, folks. Okay, we're going to talk about something called voltage, but the correct term, and I'm very bad because I'm so used to using voltage, is actually potential difference. Okay, so describe what potential difference is, and usually we abbreviate as PD rather than big V, and explain why birds sitting on the electricity wires do not get electrocuted. So, to start us off, folks, here you can see a classic picture of birds sitting on some electricity pylon wires. How can birds sit on the electric wires and not get electrocuted? Okay, if you know the answer to this one, brilliant. Check to see if you understand the physics. If you don't know the answer, let's have a look at it together, okay? So, let's start with the basics, which is the definition of potential difference. Okay, so notice again from third year to fourth year, we are now looking at things in greater detail. And I want you to remember this definition. So potential difference, PD, is defined as the energy given per charge, or joules per coulomb. So a battery of 12 volts means each energy, or each charge, sorry, is given 12 joules of energy. Okay, so another way to write that is 12 volts is the same as 12 joules slash coulombs. Okay, or if you wanted to write the units in another way, it is 12 JC to the minus 1. Okay, so the main one I would just remember is just this one here, folks. They're all the same, they all really mean the same thing, so it doesn't matter too much. So it's a bit like giving your charge a can of Red Bull to give it energy to move around the circuit. Okay, and then just to let you see that, it says the unit for voltage is not joules, but joules per coulomb. And that's a very common mistake people make, is they think it's the energy per charge. So try and remember that it's the energy per charge. Okay, so here's how we define it. Well, usually we say the energy, which is written as W, or work done, is equal to Q times V, which is charge times the voltage. That doesn't really look very useful, so I'm going to rewrite this as voltage, or potential difference, is equal to W over Q. And can you now see where we get that definition for potential difference from? Because if you think about it, remember this thing called dimensional analysis. I'm not sure if I introduced it before, but if we replace the symbols with units, we can actually get the units of the thing on the left-hand side. So work is measured in joules. That's over Q, which is in units of C. So that's joules over C, or another way to write that is joules slash C, which we pronounce as joules per coulomb. Okay, now you've seen this before because we've actually done this with speed, distance, and time. Okay, speed, distance, and time. Here's the equation. It's distance over time. So if we replace the symbols with the units, distance is measured in meters, time is measured in seconds. So it's meters over seconds, which can be written as m slash s, or meters per second. Okay, so this technique is called dimensional analysis, and it's really useful to know how to do this because it can come up in your multiple choice questions, and I'll try and show you these at some point. Now, we can apply this to any equation we want. So for example, the equation for current, remember you've just done this previously, I is equal to Q over T. So if we swap the letters for the symbols, Q, remember, is measured in coulombs, or capital C. Time is measured in seconds, and that's coulombs over seconds, or it's coulombs per second. The number of charge per second. So can you see how physics is very logical and how the equations really allow us to define things very rigorously? There's no argument about what it is, and it lets you work it out logically as well. Okay, so don't get overwhelmed by this. Like most things in physics, it's just following the same process every time. You write down the equation, you plug in the units for what you want, and then whatever you're left with is the units for the thing on the left hand side, and that's it. Good news is you don't really need to know this equation for Nat5, but I've shown it to you so you can see where this definition of potential difference comes from. Okay, and a wee reminder there, the unit voltage is not joules, but joules per coulomb, and you can see why now. Okay, and the best way I would recommend you think about this is think of it as a car, which represents the charge, going to a petrol station to put petrol in. The petrol is the energy, so however much petrol the car carries is how much energy it's got. And that ties in with our earlier model of a circuit as being like the motorway, where the motorway is the leads, the wires, and the cars are the charges which move around the roads, which is like the charges moving around the circuit. So you can think of the battery now as being like a petrol station, where we put petrol into the cars to give them energy, and each car carries a set amount of energy. Okay, so potential difference is a bit of an abstract concept, and what I mean by that is it's not something that you can see, certainly in electric circuits. It's not something you can experience directly. So here's my kind of analogy to try and help you understand what we mean by a potential difference. Okay, so we can think about the Eiffel Tower, and Mr. C, Mr. Coulomb, jumps off the top of the Eiffel Tower. What happens? Boom, and he most likely will die if he jumps off the top of the Eiffel Tower. Okay, so second scenario, what if he just jumps off from the very base of the Eiffel Tower? What happens? And a tiny boom, and most likely he'll get a twisted ankle, right? So what is the factor that decides whether he's going to die or get a twisted ankle? Pause the video and have a wee think about it, and I'll tell you the answers. Okay, hopefully you got the idea that in both cases, the difference in height is the deciding factor. If there was a big difference, then he was more likely to die because he had more energy. If it was a small difference, then he was less likely to die. It was more likely just to hurt himself because there was a smaller energy. And this is why we have the definition potential difference. It's literally a difference in potential or a difference in energy. Okay, a difference in energy. So the same is true for potential difference. It's a difference between the two energies which causes this potential difference. The same is true for gravitational potential energy. We'll talk more about this when we come to the dynamics topic. And so if Mr. C wants to survive his jump off the Eiffel Tower, he wants to do it from a lower potential. Okay, so don't worry too much if you don't quite get that analogy. I'm going to show you some worked examples now. Okay, so in general, charge will always move from a high potential where there's lots of energy to a low potential. And that's just a general rule of physics that things will always go from a high energy to a low energy. It's why if you leave a cup of tea lying out in the room, it will go from hot to cold. It never really goes from cold to hot. Okay, so in this case, our charges are a high potential, so they will naturally drop to a low potential. Okay, and that's just the general rule. Okay, so what's the potential difference between these plates? So the charge is starting at a high potential and it's going to drop down to a low potential. So in physics, the difference is always worked out by taking the final minus the initial. Okay? Think about acceleration. Acceleration is v minus u over t, the final speed minus the initial speed over time. Okay? So the final potential is 0 volts. The initial potential is plus 2000. So if I sub it into my equation, I get 0 minus 2000 is equal to minus 2000 volts. And you might think, well, Mr. Lamb, does that mean it's got negative energy? And in a sense, yes, okay? But it's not negative energy in the sense of it's missing something. The negative here is really just a label. It's a bit like how we have positive and negative charges. I didn't need to call them positive and negative. We could have just called them A and B. We could call them foot left, foot right, if we wanted to. So the negative here is just a label. Don't try and think of it as being like a negative number. So hopefully you got that. Let's try another example. So let's try a second example here. Notice we've got a positive charge here again. We have 2000 volts and we have 2000 volts here, and they're both positive. So what is the potential difference? Pause the video, have a wee go, and then I'll tell you the answer. Did you get that the answer here is that the potential difference is 0 volts? Okay, now how did we get that? Well, if you think about it, if the positive charge started here, so this is the initial, and supposing it went down the way to the final, okay, if we use the rule before, final potential difference is equal to final minus initial, then we basically get 2000 minus 2000, which is 0. So that means that the potential difference is 0 volts. Okay, and if you're thinking about our starter question, this kind of explains why birds can sit on a wire and not get electrocuted. It's because when they're sitting on the wire, you can imagine this is a single wire here. They put one foot down, okay, and they put a second foot down, and this is the bird here. If you think about it, this will be at 2000 volts plus 2000. This will also be at plus 2000. So if you take the difference, it's got a potential difference of 0 volts, which means there is no energy per charge. And so technically, there's no electric current passing through the buds. Okay. So final example, I think, what happens if you've got plus 2000 and minus 2000? Well, remember, this is the initial one. And this is the final one, because the charge will always move from a high potential to a low potential. So again, using the same rules as before, potential difference is the final minus initial. So we get that it is equal to 2000 minus, now we have to be careful here because it's a negative 2000. Okay, and hopefully you know this from maths, but if you're subtracting a negative number, it's the same as adding that number. So the total voltage or potential difference is 4000 volts. Okay, so notice how this is the biggest potential difference, and that kind of makes sense because it is literally the biggest difference between 2000 to minus 2000. Okay, so finally, how can birds sit on electron wires and not get electrocuted? It's because there is no potential difference across them, since they are sitting at the same potential all the time. Now, how can we give the bird an electric shock? Well, supposing for some strange reason we had a mutant bird and it could put its foot right down on the ground. Now, if it could do that, the ground has a 0 potential, but the wire could be at, say, for argument's sakes, 1000 volts potential. So then the potential difference would be final minus initial, 0 minus 1000, so it's negative 1000 volts. So in that case, the bird would die because it would have a massive current and voltage going through it. That's also one of the reasons where if you ever go skiing in Europe and you go to the train station, they'll always tell you to carry your skis horizontally and not resting on your shoulders where they're sticking up above your head. Because most trains in Europe are electric. So if you've got this big massive ski walking across near the train station, what can happen is those skis can touch the electric wire. That means it's now in contact with the ground. So there's a massive potential difference and you're likely to get a shock. Now, I can't remember if I said this to you in third year or not, but in theory, if you don't want to get an electric shock from an electric fence, all you do is you jump onto it and make sure your feet don't touch the ground. Because if your feet doesn't touch the ground, it's only touching the electric fence. Assuming the electric fence is all at the same potential, you won't get an electric shock because the potential difference will be 0. However, if your feet is touching the ground, there will be a potential difference, so then you will get an electric shock. Okay, have a wee watch of these two YouTube links. I'll put them in the post later on. They will explain things again in a bit more detail. The first one you might have even seen last year because it was the one with the brainiacs where they're trying to touch the electric wire to give themselves electric shocks. But hopefully you can understand it in greater detail now. Okay, and just to give you the answer, birds do not get electrocuted in this case because they're sitting at a position where there's no potential difference. The wire they're sitting on is only at a single potential value, so if you subtract that value from itself, you get 0, hence 0 potential difference. Okay, and then a final one, what can we use this potential difference from? We can use it in something called parallel plate capacitors. And that's what these look like. We'll talk more about these when we move on to the electronics topic.